Hello everyone. In this video we are going to continue our study of Laplace equation, and essentially we are going to look at some properties of the Laplace equation. Okay, so this sort of thing, we call this sort of thing as the a priori estimate. Okay, estimate. So essentially what it means is this. See, let's say I give you this equation, right? For now, let's just, this is the motivation part of it. So let us just think of it like this. Let's say I give you this equation, which is minus Laplacian of u equals to f, and that is in some domain omega. Clear? Now, see, it is not always feasible to create a solution. You understand? Explicit solutions. Basically, it's not always possible to find a solution explicitly to solve this problem. Yeah, but without doing that also, what you can do is, let's say we assume that, let's say there is a u, yeah, which satisfies this equation. Yes. Now, one thing is very certain: if there is a u which satisfies this equation and f is given to be continuous, yes, in, let's say, up till omega bar, up till the boundary of omega, if f is continuous, you do realize that then Laplacian of u is continuous. Yes, and then u has to be C2. U is C2. So whenever you have a solution that is C2, that is given. Yes. So if for this to work, you do not need to know that whether there is a solution or not. You know that if there is a solution, explicit solution basically, if there is a solution, it has to be C2, right? So this is one idea, or I mean a requirement of the solution. There are other things also that you see. The question is this: so without solving the problem explicitly, can you tell anything about solution? So let's say if there is a u which is in C2 and it solves this equation, yeah, can you say anything about this function? I mean, let's say how many such u's are there? Let's say uniqueness is there not. So let's say u1 and u2 are two solutions. Are they distinct? So can u1 be not equals to u2? This sort of question. Or there may be other questions also, that let's say what are the maximums of u1 and u2, where does the maximum attain, those sort of questions. So the first part here, we call it a maximal principle, and this is one of the most fundamental result of all of PDE. Yeah, this is the most fundamental result. So this is called maximum principle. So what is it? Again, this maximal principle, these sort of things are called a priori estimate. A priori means without knowing if there is a solution or not, we are just assuming that there is a solution. If there is a solution, then that has to satisfy this sort of property. So what is the maximal principle say? That suppose, yeah, let u of xy, so this is a function of two variable. I'm just doing it in two variable. This is true for any variable, absolutely no issues. So suppose u of xy is harmonic, okay, in a bounded domain. Okay, so this is I am talking about a bounded domain T. Clear? Bounded domain T, which is subset of R2 for now. Yeah, you can change it to Rn, no issues. Yes, everything is fine. Okay, so and so essentially we are starting with the function u, which we are assuming that it is harmonic. So what are the examples of such functions? So let's say ux looks like this: ax plus by plus c. That's one function which satisfies this equation. Or let's say x square minus y square. You can see that this also satisfies this property. So there are many different functions. Any constant will also satisfy this. So there are many different functions which satisfies this thing. There is basically harmonic in some domain T, which is subset of R2. Okay, and continuous in D bar. What is D bar? D bar is D union the boundary of T. Clear? So basically up to the boundary. Clear? Now the thing is this: then what happens is, then the maximum of u, yes, maximum of u is attained on the boundary of omega, sorry, boundary of t, which is nothing but del t. What am I saying is this? See, let's say you have a domain D. Yeah, D. This is your domain, subset of R2, and domain means this is open and connected. Yes. As an example, you can think of this mod xy, so set of all xy's such that this is less than 1, the modulus is less than 1. That's a unit ball, right? And that is an open and connected set. Okay, now the thing is that you see this is your D, this is your D. Yeah, now in this case what is del D? Del D is nothing but the set of all x, so tuple xy such that mod xy is equals to 1. So that is your boundary. Clear? So this is an example. Now generally speaking, you have an open set and there is a boundary of it. What is the boundary? It is given by del D. Clear? Okay. Now the maximum of u, what it is saying is this. See, u is continuous in up to the boundary. Okay. So u is defined here and also on the boundary. Yes. And it is also continuous, right? Up till the boundary. Yes. So you see, if D is a open bounded set, then D union D bar, this D union del D, yeah, this set is a closed and bounded set. It's a closed and bounded set. Yes. Okay. Now, if it is a closed and bounded set, U is a continuous function on a closed and bounded set. So we know that such functions attains a maxima and a minima on the set itself. Okay. So essentially, what it says is, you see, U will attain, this is a guarantee, U will attain its maximum slash minimum. Both maximum and minimum will be attained on the set D union del D. Clear? So we don't know where exactly, it may be on the boundary, it may be on the interior, but it is always going to attain. This is the property of continuous functions, right? Continuous functions. But the thing is, here the function is more than continuous. It is saying that U is also harmonic inside the domain, right? So what is so special about harmonic thing? It is saying that the maximum will always be attained somewhere on the boundary. It can't be attained on the interior. Is it clear? Okay. So physically, what does it mean? Let me do this part physically. Yeah? Maybe I can put it in red. So physically, it means that the temperature of the body, let's say, so in this case, let's say U is modeling the temperature. The temperature of a body, which is neither a sink or a source, neither a sink or a source. Okay. So basically, I am starting with a body which is neither a sink and the source of it acquires, okay, its largest and smallest value, okay, on the surface of the body. On the surface of the body. Is it okay? It can't be in the interior. So that's your physical interpretation. So I hope this is clear. So basically what I'm saying is this: if you have a body, let's say, and that body is neither a sink and the source of the heat. So basically the temperature of the body, what happens is, in this case, definitely if this is not a sink or a source, so basically it is not letting any heat come in or go out, right? So basically it's then if you look at the temperature of the body, that temperature will always be acquired either on the surface of the this thing, so the maximum temperature, and the minimum will also be attained on the surface itself. Okay, that's what it physically means essentially. Okay, so let's look at the proof of this thing. Of course, the proof is not important for examination purposes, but the thing is, this is a slight analysis, because all we were doing in this course up till now is essentially solving some problems. I think it is better for just a change of test, and it is actually important for you to know what's exactly happening. So let's say that as I told you, you see, U is a continuous function. So, and D union del D, this set is a closed bounded set, right? It is a closed and bounded set. Why closed? See, D is open, but D along with its boundary, if you take, that will give you a closed set. And of course, this is bounded, it is given, you see, bounded domain. Clear? So these assumptions are all required. Yes. Okay. Okay. So let's look at the proof. So let's say that there is a point x naught. Yes, so first of all, what it is saying is this: the maximum will be attained on the boundary. Clear? Yes. So we have let us suppose that the maximum of del D, yeah, so it attains at a point. So let's say maximum of u, okay, over where? Over this thing d. Okay, I will put a small notation here: d union del d. I will call it a del d bar. Clear? This is what the notation is. So maximum of del d bar, let's say, that is attained at some point which is given by u of x naught y naught, okay, and x naught y naught is in d. Clear? So in the open set, yes, it is not neither in the boundary. See, what I am saying is this: the maximum will be attained on the set d union delta d, right? So let's say if I can show that the maximum, if I am starting with the fact that the maximum is attained on del d, this set, open set d, and if I can show a contradiction, it means the maximum has to be attaining somewhere on the boundary, right? Okay, so let's start with the point where it is maximum is attained. Now, if this is the case, and let's say this is equals to a maximum is given by m, that's the maximum, right? Number m. Yeah, it can be positive, negative, we don't care. There is some number m. Yeah, let's just assume that. Okay. And let's say yes, and let's say m bar is the maximum of u over maybe I can do it like this. Yes, one second. Let me change it to okay, let me change it to, so m bar, let me do it like the maximum over d bar. Okay, let's do it like this.